All right, welcome back. We've got a big section here. It includes a couple different topics. By the end, our main goal is to make HTTP requests from JavaScript from the client or from the browser. So load data from an API, send a request somewhere. So very important stuff that you do all the time if you make single page apps, and in the projects that we build later on, there's at least a couple examples where we're working with HTTP requests in the browser. But before we do that, we'll talk about promises and how we use promises to manage asynchronous code and make our life easier. But before we do that, we're going to talk about asynchronous code or async JavaScript, what it actually means. And in order to do that, we need to understand how JavaScript works behind the scenes. At least we don't have to go crazy into detail, but we need to understand the basics. So that's where we're going to start. In this video, we're going to talk about something called the call stack. So the call stack is a tool or a feature of JavaScript. It's also something you see in tons of other programming languages. What it does is it helps JavaScript keep track of where it is in your code. If you have multiple functions and some of those functions may call other functions, which often we have functions that call functions that call functions, the call stack is the mechanism by which the JavaScript interpreter keeps track of its place. It's how JavaScript knows which function is currently being run, which functions are not done yet, what's waiting on results or return values. You can kind of think of it as this diagram here. If your script with a bunch of function calls is a massive book, the call stack is the bookmark or your finger that you use to figure out where you are, to keep track of your current place. And before we go into any more detail, let's talk about the stack part. I think call in call stack makes some sense. It has to do with function calls, which functions are being called, what is or what's been called, what is waiting on a result to come back. The stack part has to do with a data structure in computer science called a stack. A stack is a very simple data structure. All you need to know is that just like a stack of books on your desk or a stack of plates on in your sink, the last thing that you put in is going to be on top, and that will be the first thing that you remove. So the last thing that was added, the most recently placed item, in our case this apple on top, will be the first thing out. You don't grab from the bottom of a stack of papers, you grab from the top, the most recently added thing to that stack. And that's important because that's how the call stack works. So we're going to walk through a simple example. Here's what you need to know. When a script has some number of function calls, the very first function call that the JavaScript interpreter hits or reaches will be added to the call stack. That function will be carried out, and if there are any other function calls within that first function, they will be added to the top of the call stack. And that continues until one of those functions returns a value, at which point it's removed from the stack. It's gone. And then the function that came before it will hopefully finish. Maybe there are some other function calls, in which case those are added to the top of the stack and then removed or popped off as they complete. I think this will become clear if we have an example. So on the left, I have a couple different functions. The first one is called isRightTriangle. It accepts three different arguments, A, B, and C, three different numbers, and it should return true if A and B, if you square them and add them together, you get C squared. A squared plus B squared equals C squared. So if something is a right triangle, the third value here, C, would be the hypotenuse. These two would be the other sides. I can't remember what they're called, but we have two sides on a triangle and then the hypotenuse in a right triangle. So 9 would be 3 times 3, 16, 4 times 4, and 25, 5 times 5. And that indeed would be a real right triangle. 9 plus 16 does equal 25. Okay, so isRightTriangle is not a function that just returns something immediately. It needs to call other functions. It's going to return if the square of A plus the square of B is triple equals to the square of C. So square of A needs to be called, and that in turn calls multiply x times x. So we pass in 3, multiply 3 times 3, which is a different function which returns two values, the product of them. So when the interpreter encounters the very first function call, isRightTriangle 3, 4, 5, it's added to the call stack, which is what I'm representing over here. And we can't just get a value back immediately. There are multiple function calls in here that happen first. So square of A, which is 3 in our case, square of 3 will be the first thing to be added to the call stack, which is what this slide is. Square of 3 does not return anything either. it calls a different function, multiply 3, 3, which I'm showing here. So then multiply is added to the stack. So this function has not finished running. This one has not finished. This one doesn't call any other functions, so it returns 3 times 3, which is 9. And when it returns a value, it is removed from the stack. The last thing in is the first thing out. So then square of 3 now has a value back from multiply, which was 9, so it can return that value. So it's popped off. Now we end up with isRightTriangle. That's the current function that is being executed. It's been waiting a while because a while is relative, but I had to wait for 2 other function calls to return. So now you can kind of fill in the blank here. The first part, square of a, square of 3 is 9. We have a value. Then it moves on. All right, is there another function call? Yep, there is. Square of 4, which is b. So square of b. So square is added to the top of the call stack. And when I say top, it's not really a top and bottom situation. It's just a data structure. Think of it kind of like an array, but much simpler. But I'm just using top and bottom here to help explain visually what's going on, like a stack of books. So square of 4 doesn't return a value, right away at least. It has to call multiply 4, 4. So that's added to the top of the stack. That does return a value, x times y. 4 times 4 is 16, so that pops off the stack. Then square of 4 now has a value for this. It fills in that blank, 16, which means that it's done because it returned 16. And then we fill in the blank in isRightTriangle. We now have this done, and then we have our triple equals square of c, square of 5. So 5 is added to the call stack. That doesn't return a value yet. It has to figure out what multiply of 5, 5 is. So that is the next function call added to the call stack. That returns 25, which means that square now has a value, so both of those are popped off. And then we end up with 25 here. No more function calls. Now just some simple math. And actually the order here, it probably evaluates this first anyway. 9 plus 16, it doesn't actually matter here. We're just talking about function calls, but we end up with 9 plus 16 triple equals 25. That is true. So this function finally returns true, at least in this case. And it is popped off the stack. The call stack is empty. It returns true, and we're done. So that is a brief intro to the call stack. In the next video, I'll show you an example of how you can actually see it using the dev tools, or at least a representation of it with your own code, and you can step through it step by step. All right, so let's do that next. Okay, so that was a brief intro to the call stack. Now I'd like to show you in the Chrome DevTools how you can actually take a look at the representation of the call stack and step through it one call at a time. So let's do it. I have some simple code here, a function called makeRant that I'm calling twice. I'm passing in a string, the rant text, and then a place to append a new h1. What it does is it makes a new empty h1, then it sets the inner text to the result of a function called getRantText. GetRantText is going to call 2 different functions. The first one is scream, which uppercases it and adds some exclamation points. Then another function I call repeat. Yes, there is a built-in string repeat these days, but for this example, I'm not using it. I wanted a couple other functions on the stack. So then it calls repeat, which takes that scream, the uppercased version of whatever we pass in. So let's say we started with go away. That's our phrase we pass in. It's going to call scream, which will give us go away with 3 exclamation points. And then if I call repeat, which I am here, getRantText repeats it 8 times, we end up with a string that looks like this. Whoops. 8 of those. Then we take that and create a h1, which we actually already created. We add that as the inner text and append it to whatever element we pass in. So it's just a dumb demo. It's not something you probably would do, but this is what we end up with over here. I have 2 h1s. I hate mayonnaise. Very true. I hate mayonnaise so much. Oh my gosh. I feel queasy even just writing the word, let alone seeing it 8 times here. That's coming from makeRant. I just passed in the string and a place to append the new element. And then here's the second one. If you have to cough, please cover your mouth. It's also being appended here. Let's take a look at just one, so it will make it a little easier when we step through the call stack. So I'm going to open up the Chrome DevTools and go to the Sources tab. And in the Sources tab, I'll pretend that was closed. If we open up this navigator on the left side for me, go to our file with the code. So app.js is the name of my file, whatever you named yours. What we do is add in a breakpoint. On the left, I can actually click. So if I click in here, I can make some changes and play around with them. But if I click on the number to the left of one of those function calls, it will actually insert a breakpoint. It will pause execution of our code when it encounters this. So all of this code will run first. If I were to add in a console.log hello, and refresh the page, well, I'm an idiot, it goes away. Of course, I just said that. If I do a console.log here, hello, this will run first before we encounter that breakpoint. If I look at my console, we get hello. Notice though, I don't see anything over here. It says paused in debugger. And I have this little alert over here that says paused on breakpoint. So because I clicked there, it paused. If I unclick and refresh, it doesn't pause anymore. But if I click and I refresh the page, there we go. Okay, so let's see what we can do. On the left side, we have a tab or a piece called call stack. This is where we'll see a representation of the call stack. And if we just walk through this first on our own, I'll zoom in a bit. Can I zoom in? Okay. I'll close the sidebar. Make rant is going to be called. There's no function calls aside from make rant so far. So make rant will be added to the call stack. Then make rant itself calls document.createElement is a built-in function or method that won't appear on the call stack really. But our first function we defined is get rant text. So get rant text is over here. That calls scream. So scream will run and return something. Then we get to rant, and that's returned. We have text. Then repeat is called with that value. So repeat is going to run. So let's just play around with it. I'm going to click over here on this. There's also a shortcut, but to make it easier for you to see when I'm actually advancing, I'll just click. So keep your eye here where it says call stack. Okay, so make rant was added to the call stack. It's not done executing, otherwise it would be off. And it can't be done. It has to do some other stuff first. So the first thing it did was evaluate this document.createElement. Then we get to this line, get rant text. So you'll see get rant text is now added to the call stack. And if I look at any of these at any point, if I click on make rant, you can see it's kind of hard to show here, but this is the information, the values that are current in this scope of make rant. So phrase is set to I hate mayonnaise. That's the argument we passed in. We also have element, which is the body, which I passed in down here. And now this h1 variable is this h1 element that we created with document.createElement. So then instead of get rant text, we have a variable text, but it's not set to anything yet. If I move forward again, we'll see scream added to the top of the call stack. There it is. So make rant started, but it's not done. It can't finish until get rant text comes back. That can't finish until scream comes back. We're in scream right now. Scream does not call any other functions aside from returning string.toUppercase. So you'll see if I advance again, scream is up top, advance, and it's gone. Scream has been removed. It finished executing and it returned a value, which we now have here. Text has value. I hate mayonnaise, all uppercase with 3 exclamation points. That came from scream. Then next line, rant, the variable let rant equals repeat of text. This is text, that variable. So repeat this 8 times. So repeat is going to be added. That's our next function. You'll see it added to the stack. There it is. So get rant text is still waiting. Make rant is still waiting on get rant text, which is waiting on repeat. So repeat is then going to loop. I'll skip through this. So we have result, which is completely built at this point. The loop is over. We're now at return result. So result is I hate mayonnaise, uppercase, exclamation points, repeated 8 times in a single string. That is returned. So the contents of the function don't really matter in these examples. I just want you to pay attention to the call stack itself. Watch when things are added and when they're removed. So return result, repeat should be removed. And there we go. So now getRantText has all those function calls. It has return values from them. It's done and it's ready. Well, it's not done yet, but it's ready to return rant. So it waited first to get scream, then scream came back and it waited to get repeat, then repeat returned a value. So now it can return that value. So it's going to return and getRantText will be removed. There it goes. Goodbye. Now we're back in makeRant, the original function call that has been waiting patiently this whole time. So you can kind of see where I was going with this, where are you? This idea here of a finger in a book to keep track of where you are. It's kind of the same idea, maybe. I don't know if that's a good analogy or not, but it's kind of the same idea. This function was originally added to the stack a while ago, but it couldn't finish until a bunch of other function calls ran. And this is a simple example. Often you'll end up with some functions that have a whole bunch of function calls which call other functions, and then recursion is a whole other issue, which we're not going to get into at this point, but just know that this is a simple demo. Most of the time your apps are going to have many more functions on the call stack at any given point, or they could at least. So makeRant is now ready to append element.append child. There is no return statement in makeRant. So there we go, we get to the last line, it's showing me this here. So makeRant will be removed from the call stack, and because this element.append child h1 ran, we now have the text showing up, our new element on the screen. So I'll step through it, and it's gone. It's completely off the call stack, which means that this function call here is done, it finished. That was the original starting point. Now the interpreter has moved on to this line, and there's nothing after it. It's just done. And there we go, we made it through. So that is how you can use the DevTools to step through, step by step, each function call on the call stack and see what's going on. And this can be useful if things are just behaving very oddly. It's also a nice way, if you had a breakpoint somewhere, for you to just take a look at the values at any given point, play around with the variables in there, see what's going on, diagnose your problems. But the main reason I brought it up here was just to make it clear how the call stack works. This idea of the latest function call to be added to the stack, that function call will be the first to be removed. And you end up with this pileup of functions that are function calls that maybe are waiting on a bunch of other function calls to finish, which themselves might be waiting on other function calls. And eventually one of them has to finish and return something so that sort of a reverse cascade can happen. The functions that were waiting will hopefully return, which continues all the way down to our original function call, which was makeRant. So why are we talking about this? Why do you need to know about it? Well, it's going to help explain and help you understand how asynchronous code works in JavaScript, which is what we're going to tackle right now. Well, next video, right after this. Okay, so we talked about the call stack. Put that aside for just a moment. Next, we need to address a fundamental characteristic of JavaScript as a language. JavaScript is a single-threaded language. If you don't know what that means, don't worry. All that it really means is that at any given point in our script, whatever script is being executed, JavaScript is running one thing at a time. It's not multitasking. It does one thing. There's a really good blog post, I think it's on the Google, one of the official Google developer blogs, talking about asynchronous JavaScript, that humans are multi-threaded. You know, you can fold the laundry while watching TV or talking to your friend or whatever it is. But humans are single-threaded in one very specific case, according to this blog post, which is when we sneeze. No one can do anything else except sneeze. So when you're sneezing, that's the one thing you're focused on. So back to JavaScript, at any given point, one thing is being run at a time. And this has a whole bunch of implications, but let me just demonstrate it first. If we do something extremely simple, we console.log I happen first, and then a different console.log I happen second. And if we alert in the middle, alert hi there, and I run this code, what will we see in our console when I refresh the page? Well, let's refresh it. There we go, I get the alert. We open up the console. It won't even let me open it, will it? Well, let's try it one more time. I'm going to refresh. We get I happen first, and then hi there, and it just stops. This alert is blocking everything else from going on until a user finishes it or completes it, at which point JavaScript moves on to the next line. So that's a simple example, but here you can tell JavaScript is doing one thing. When it's alerting, it's not continuing to console.log, or if we had math after this or a different function call, it's not going to move on. And that seems like it could be a severe limitation. If we do things that take time, if we do things that aren't immediate, we don't want to just have a user sit there waiting and have no other code running. But as you've probably seen already, we have a way around this. And we'll get to that in just a moment. But here's a simple example of something that we do via JavaScript all the time. We send a request. From the browser, we write some JavaScript code asking for, let's say, data from a movie API. That takes time. It sends a request to a server. That server may or may not be online. We may have a valid endpoint, we may not. But even if everything goes great, it still takes time. The server will respond to your request. If we're looking for movies that match the query BAT, B-A-T, it will search through its database, find the relevant information, and then send a response back. Bates Motel and Batman in this case. Again, this takes time. It can be very slow. So what happens to our application? Does it just stop and nothing else happens? Like what we had over here, where this alert potentially takes a long time for a user to finish. A user may not notice it. Even if it's just a split second, your code is just doing nothing right now. Is this what happens when we make a request? When we are fetching data from an API, when we're trying to save data to an API? Anytime we do some sort of single page app functionality, which usually involves communicating with an API, communicating with a database or a server, that takes time. Is our app just going to sit there doing nothing? And is a user just going to sit there waiting for something to happen? The answer is no. How does that work and why not? That's what we're going to answer in the next video. JavaScript has a couple tricks up its sleeve, or rather the browser has some tricks up its sleeve to get around this single-threadedness of JavaScript. So to summarize what we saw here, in JavaScript, at any given point, JavaScript itself is running at most one line of code. So it's not multitasking, it's not doing three things at once, it's doing one thing at a time, or nothing if it's not doing anything. It's very important to understand that so that you can better understand the workaround we have, which we're talking about right after this. Okay, so we established that JavaScript is single-threaded. That means it's doing one thing at a time, like a human sneezing. A human does one thing, which is sneezing. It's very, very difficult to also talk while you sneeze or eat while you sneeze. Although, I guess I have been driving and sneezed, and I continued to drive, but I basically just prayed that I wouldn't crash because all I could do was sneeze. So JavaScript does one thing at a time. As we mentioned in the last video, a lot of the time we do things that take a lot of time. That's a bad sentence. Commonly, we do a lot of things that take time, whether it's getting data from a database or an API, or trying to save something, or even just set a timer. How does something like a timer work in JavaScript? So here's a simple example. This is not exactly full code that would work. I've made up a function called save to database, but imagine we're doing something like this. A user types something into a form, it submits. We want to grab the value from the form, save it to a database, and that could take a couple of seconds. It could take half a second, it could go really fast, it could take 10 seconds and fail. Does this line just not run until this finishes? Well, we have a workaround. We've seen this a couple times before. We've actually seen it a lot. For these processes that take time, we pass a callback function, and those functions will be executed at the appropriate time after this interval has passed in the case of a set timeout. But this doesn't really answer the question of how does it work or why does it work. We know that this does work. Set timeout for 3 seconds. We'll wait 3 seconds before running this code. But how is JavaScript going to know? How does it set a timer for 3 seconds if it can only do one thing at a time? That is what we're going to talk about here. If we go back to this example where we had our first console.log and then the alert blocked everything else, JavaScript is fully focused on the alert until it's gone. Then we move on to the next console.log. Why, if I replace this with a set timeout, pass in some function where we console.log I happen third, and then an interval or a delay, 3 seconds, 3000 milliseconds. Why does this work? It seems like it shouldn't. Like nothing different is really happening except we're passing in some function to be called later. But based off of what I've told you, it seems like this should run. Then JavaScript encounters this line which says set a timer for 3 seconds. That should just take up JavaScript's full capacity to focus on anything. It should just be setting a timer. How can JavaScript keep track of 3 seconds and remember to do this or call this function while also moving on to this console.log? Remember, that is printed out immediately, and then 3 seconds later, this is going to print out. So if I have other code down here, I could have a whole bunch of other stuff. That's all going to run, assuming that it doesn't take more than 3 seconds. That will run before this. Doesn't seem like it should be able to work. Seems like JavaScript should have to focus entirely on keeping track of 3 seconds and knowing when to actually execute this. But we have a workaround. The trick here is that the browser does the work. JavaScript is not the same thing as your browser. JavaScript is a language that is implemented in your browser. But the browser itself, like Chrome, Safari, even Internet Explorer, our good friend, when I say good friend, I mean worst enemy, those browsers are written in usually C++, a different programming language. And the browser itself is capable of doing certain tasks that JavaScript sucks at, or things that take time. They're handed off to the browser. So JavaScript says, here is this thing I need you to do for me. The browser takes over. And then when it's done, it reminds JavaScript, okay, your turn again. So this is a really key thing to understand. JavaScript is not setting a timer or keeping track of how many seconds have gone by. JavaScript is not sending a request to an API. The browser actually handles it. And this is something that, honestly, I went a long time without understanding about JavaScript. And it's not crucial to being able to make a request or use set timeout. You've already done that in this course. But I think it helps a lot to understand why we use callbacks and why we get to things like promises and async functions. So browsers have a set of these APIs called just generally web APIs. And they can handle certain tasks in the background, like making a request. That takes time. Set timeout, which we saw here, that takes time. The browser is capable of doing those things in the background. So JavaScript is going to encounter certain lines of code, like this line. JavaScript knows how to do that. Then it gets to set timeout, and it's going to pass it off to the browser and say, please remind me after 3 seconds has elapsed, or hey browser, you set this timer for me, and when you're done, give me this function back. So that's why we pass a callback. It just keeps plowing along. It hands this off to the browser. The browser is in charge of keeping time. And then it reminds JavaScript, hey, here's that thing I want you to do, or you wanted me to remind you of. So JavaScript doesn't get hung up. Its single thread isn't blocked by this set timeout because it's passed off to something entirely different. It's passed off to the browser. Then that callback function, in the case of set timeout, when it's time, when 3 seconds has elapsed, the browser is going to take that function, the one that just console.log something, and put it on the call stack. So this is where the call stack comes back in. So let's take a closer look with some diagrams. Here we have similar code, I think different text. I print first, I print second. Is that what I had? Oh, okay, I capitalized it here. It doesn't matter. So JavaScript is represented by this JavaScript logo. It's going to encounter this line. The interpreter sees this line. It knows how to handle it. Console.log, I print first. It runs that. Then it gets to set timeout. Set timeout is something that the browser will do for us, or it will do for JavaScript. So this is my personification. Hey browser, can you set a timer for 3 seconds? The browser says, sure thing. So remember, this is separate from JavaScript. This is the browser itself setting a timeout, keeping track of 3,000 milliseconds. So then JavaScript is free to continue on. It doesn't have anything in its call stack that has to do with set timeout. Instead, it moves on to console.log I print second. So it prints that out. And there's a little time icon over here that signifies 3 seconds have elapsed. Now the browser says, time's up JavaScript, make sure you run that callback now. And it places the callback, this function right here. I used an arrow function in this example. I just used a regular function expression here. It places that function back in the call stack. So JavaScript knows, oh, I need to do this thing. So JavaScript does not keep the time. Same thing with making a request. JavaScript does not make the request itself. The browser and its web APIs they manage all of that, and they simply tell JavaScript, they add to the call stack when it's appropriate. Here's the next thing for you to do. So JavaScript then now has a new function in the call stack, and it executes it, and at console.logs, I print after 3 seconds. So understanding this relationship will help a lot once we get to promises and actually making requests. JavaScript can only do one thing at a time. It's single-threaded, but in special cases, when we are doing things like setting a timeout, requesting data, or adding an event listener to a div, an li, JavaScript isn't going to sit there and just listen nonstop to see if something's been clicked. That's handed off to the browser. And the browser is in charge of deciding when to actually add a new callback or a function to the call stack for JavaScript to execute. Here's this really cool website I found that helps explain how this all works. So you can type code over here. If you do play around with this, it's called loop. It doesn't work well, or it doesn't work at all if you use arrow functions or any of the newer JavaScript syntax. So just stick to some basic stuff. But here's what it does. It actually slows down, or it mimics the execution and what happens behind the scenes with JavaScript and the handoff to web APIs, which is what this box over here represents. Here's the call stack. Here's web APIs. So JavaScript is going to encounter this line, the interpreter. It can run this immediately, and it will console.log, hi everyone. Then it hits set timeout, and you'll see visually that the web APIs takes over. And you'll see visually that the set timeout, the interval or the delay, is being kept track of over here for 7 seconds is what this one is set to. And then another set timeout, this one for 3 seconds, will also be handled over here. And in the meantime, JavaScript will move on. If I add in, let's do at least one more console.log by for real everyone. JavaScript moves on to this, and then when the browser, the web APIs over here, decide or calculate that the time is up 7 seconds or 3 seconds, they add the callback here, not directly to the call stack. They add it to something called the callback queue. We don't have to get too far into the weeds here, but essentially this is a place where callbacks are added, and JavaScript will draw upon this queue. It's a way of JavaScript to know, okay, what's something that I need to do next that is coming back from the web APIs. Okay, so let's see what happens when I click save and run. I'll pause. First thing, call stack now has one function call, console.log hi everyone. Okay, simple enough. So it does that. Now it gets to this set timeout function that is added to the call stack, but JavaScript realizes, oh, this is one of those things I can hand off to the browser. So it doesn't take charge of this. It hands it to web API, the web APIs. There you go. So it doesn't run the code. It doesn't run the callback. Oh, I just broke it. Okay, let me pause again at the right moment. There we go. There's a timeout that is being kept track of over here, and JavaScript moves on to the next line, which is another set timeout. So the same thing happens. It's added to the call stack for a moment. JavaScript then passes it off to the web APIs and says, okay, when that interval or that delay is over, give me that callback back, and I'll execute it at the right time. So we resume. JavaScript moves on to these two console.logs. There's the first one, the second one, they both run. And then the 3-second timeout finished. Now there's only one over here, the 7-second one. The 3-second one finished, and it added, the web API added that callback here, which is supposed to console.log oink oink. It added that to the callback queue, which JavaScript will now draw upon. And you'll see that did I not click resume? There we go. Those functions are then executed one at a time. They both console.log, and we're done. So let's do it one more time. Just quickly, I won't pause. You can see the web APIs take control of those timers. JavaScript moves on. It has one thread. It keeps going, and then it draws upon that callback queue when the web APIs have placed one of those functions in the callback queue. That relationship is very important to understand. So let's pause, and now I'll have my console open so you can just see the whole thing as they get printed. So we get hi everyone, then the next line, which will be bye everyone, then bye for real everyone, then that first callback, the 3-second one, is added to the queue. We get oink oink, and then the 7-second interval or timeout finishes, so we get moo. Okay, so I'll stop here. Like I said, this is a very fundamental part of JavaScript. This is why we use callbacks all the time. This is how we get around the fact that JavaScript is not a multitasker. It does one thing at a time. So when we pass a function as an argument, as a callback function to things like set timeout, which the web APIs handle, those functions are not called right away. JavaScript doesn't worry about it. JavaScript just passes it off and continues on its merry way until the web APIs at some point place that function in the callback queue, where JavaScript then draws upon and says, oh, okay, you want me to do this thing, I guess it's time. So it does not do the hard work of keeping track of time. It doesn't do the hard work of making a request. And that's why we use callbacks so frequently for these asynchronous things, these functions that take time. And I need to make that clear because now we're going to go more into async.js. We'll talk about how we make requests, and that takes a lot of time, and sometimes it sucks to write a ton of callbacks, which is where promises come in. So this has been setting the stage. I think it's very important to do. I have taught promises and async functions without really going into detail of how this works, but I think this will help, I hope. And please leave some feedback if you think I'm just confusing you or it's not really relevant, because you absolutely can learn this stuff without understanding what the web APIs are and the call stack, but I think it will help, maybe. So let me know. All right, I'll be quiet, and next we'll move on to talking more about callbacks, some of the problems with having a bunch of callbacks, and how we can get around them with promises. All right, welcome back. So we saw why callbacks are so important in JavaScript. We pass a callback in to certain functions that the browser takes over. Things like set timeout, set interval. Also, when we make requests, different ways of making requests we haven't really covered yet, the browser takes care of that, and we pass in a callback. But callbacks are not perfect. They can get messy very quickly, which is what I want to show you here. I'm going to show you a way of doing something with callbacks, and then we'll see how to refactor it using promises. So this is finally the ramp up to promises. Let's write a simple function that will take a number of pixels and move our button over that number of pixels, and it will do it after a delay. So we could do like after a second, move it, after another second, move it, and so on. So I'm going to start by selecting the button. It's the only button on the page. So const btn equals document.querySelector button. Then all we're going to do is change button.style. I'll do it with transform this time. I think at some point in the course I did button.style.left and top, which is not really the most performant way of changing a position or moving an element around. Transform is better. And if you're curious why, I have a YouTube video you can check out on it. It's called The Only 2 CSS Properties You Should Animate. The short story is that when you transform something, it happens much later in the browser's rendering process. It's much easier for the browser to move something via transform rather than changing left, which causes a re-render of a lot of different things. Anyway, so I'm just going to do this. We'll move it left to right, so I'll just do translate x and pass in a number like 100 pixels. And let's just make sure it's moving. Okay, so now I want to do this inside of a set timeout. So it only happens after, let's say, 1 second. So set timeout, and then I'll pass in a function, just do an arrow function here. My duration will be 1000 milliseconds, and I'll move this right there. So now I refresh, it should start on the left, and then 1 second later, it moves. That works great. Now, if I wanted to wait another second and then move again, maybe 200 pixels this time or some other number, I would need to nest that function call, the set timeout, inside of this set timeout. Otherwise, if I just have a second set timeout, I mean, I guess you could do this and just keep track of the number of seconds, but this is not ideal. We'll see an expanded version of what we're doing now where this wouldn't work. But yes, technically, if you want this to run after 1 second and this to run a second later, you could do 2000 milliseconds, but we're not going to do that. So in here, we add another set timeout. Same thing, we add in our callback, our duration. Let's do 1000 seconds, or let's do 2000 milliseconds. So 2 seconds, and then this same line, I'll just duplicate it. And I need to change what we're translating it to. Let's do 200 pixels. So I'll refresh. A second, it moves. Another 2 seconds, it should move again. Cool. And I could keep duplicating this. I just have to keep nesting if I want to make sure that this is happening after this happens. So we have our first set timeout for 1000 milliseconds. It does this, and then as soon as that happens, it sets another timeout for 2000 milliseconds. And then again, let's just do 1000 for each of these. Let's translate 300 pixels, This isn't so bad because it's such a short thing that we're doing, but it is a lot of nesting to achieve this. Let's go 5 levels deep. Okay, so now I have 5 different set timeouts, all of them 1 second long. Let's go 1, 2, 3, 400 pixels and 500 pixels. Let's check it out. It should move across the screen 100 pixels at a time, 1 second at a time. Okay, so this is relatively readable. It's not too bad. It's kind of obnoxious to have to keep nesting them, but this is not as bad as it will get. Let's put it that way. So if I want to rewrite this as a function, I'm doing kind of the same thing every time. If I want to make this a separate function I could call, what I need to do is first define my function and come up with a reasonable name. Let's call this move right. How about just move x, because then we could pass in a negative number to go the other direction. We'll do element, the thing that is moving, so our button, an amount, and then a delay. And then we'll do a set timeout. And then in here, our function, we'll put the delay right here. So that will be some number we pass in, like 1000. And then instead of button.style.transform, it will be element.style.transform equals, and then a string. I'll do a string template literal, translate x, and then I'll put in my amount that was passed in, and then follow it by pixels, just like that. So if I comment this out and I just call this one time, move x of button, let's go with 600 pixels, so 600, and after 2 seconds. Let's see if it works. So 2 seconds go by. Okay, it does move. Now here's the tricky part. If I want to then replicate this behavior, where we could have something happen after this, or after the delay, immediately after we change the transform, I want another set timeout. It doesn't really help me if I just manually set it here. What we would do instead is pass in a callback. So we would write our function to accept a callback. We could call it callback. And then all we do is execute that callback function inside the set timeout. After we do this, we call the callback. Same idea that we have here, but now what we need to do is pass in a callback. So we would pass in a function. I'll do an arrow function. Whoops. Like this. And we'll just call move x again. Button, let's go 100 pixels this time. We'll replicate the same behavior, so 1 second. Another 200 pixels after 1 second. Let's just see if that works. We will run into an issue with what I have here because I haven't passed in a callback. So we could do something simple like if callback. Okay. And let's see what happens. It appears to work, right? So we did 100 pixels and then 200 pixels after a second. And we could pass in yet another callback if we want to continue to chain these. So move x, button, let's go for 300 pixels, 1 second, and let's actually do 4 or 5 levels. Button, and then 400 pixels, 1000 milliseconds, and one last one. Move x, button, 500 pixels, 1000 milliseconds, no callback. Here we go. There we go. Keep moving. Awesome. Okay. So we wrote a function here that accepts a callback and a delay. It does something after that delay inside the set timeout. That delay is variable. Right now they're all the same. And then it executes a callback if we pass one in. And our callbacks are these arrow functions. So this is one callback. This entire thing here, from this curly brace to this curly brace, nope, this curly brace to this curly brace, that is the callback for this first move x. So this entire thing from this yellow curly brace down to here is the first callback for move x. The first time we call move x, that function call, those parens go all the way down, right? This is our initial function call, and then we have our callback in there. And then that itself calls move x, and then that has a massive callback. All this nesting, it's still not that horrible because we're just doing one thing each time. You can look at it. It makes it clear you're doing this, then this, then this. But here's where it's going to get trickier. Let's rewrite our function so that we check if the element is going to go off the screen. And if it does go off the screen, we can do something else. Maybe reverse it, or just console.log, or just stop. We won't do anything. And this is a really common pattern when we're working with asynchronous code. Often we'll send, let's say, an HTTP request. The term is request for a reason. We're attempting something, we're asking for a web page. We may get some successful response, or the server might be down. We might have an invalid URL. Your internet might be down at home or on the computer. So it's a request. And that request, let's just say this was the name of a function to make a request. Whoops, autocomplete there. That request will accept two callbacks, a success callback and a failure callback. So you can have two different branches. If the request works out, here's the code that runs. If the request does not work, here is the code that runs, the code to handle an error, for example. So why don't we mimic that functionality here for moveX instead of just moving no matter what? Let's check if we are going to move off the screen. And if that's the case, we won't do this. We won't call the callback. We won't move further. We'll do something else. We'll pass in a potential fallback or an error callback. So I'm going to rewrite this here. The logic to check if we're moving off the screen is not that important to what I'm showing you here, but basically we want to get the width of the screen, document.body.client width, and we'll save this to a variable. Let's call it boundary, body boundary or something. Then I'll show you a new method we haven't seen before. There is something called get bounding client rect. Let's test it out first in the browser. So I have a button right here. It's moved already. I won't refresh the page. If I call up that button variable and I call, let me zoom in here, button.get bounding client rect, which is a method for rectangle, rect, get rect. Here we go. It returns this object. It's called a DOM rect, DOM rectangle, and it tells us information about this element. So we can see its width, 225 pixels, 0.875. We can see its right, let's see, 733. Is that correct? Let's try moving it further. So let's do the same thing. Why don't we, on our last step, why don't we move 600 pixels over? So instead of 400, we should be 600, or instead of 500, I mean, we'll go 600. So currently it's at 733.875. If we refresh and let it do its thing, just wait here, kill some time. Let's see what we get now for the right. The right is now 833.875. And if we call move X again, button will move 800 pixels. And 1 second is fine, no callback. We wait 1 second. Now let's look at our get bounding client rect. Right is 1033. And what is our entire width right now of the body? Document.body.client width, not height, but width, 1132. Okay, so we're close. What we want to do is compare those two. The right, if we're going to the right at least, we're just worrying about moving to the right. So we'll check if the right is greater than or equal to this boundary here, which we already have, document.body.client width. And that will change depending on the screen and if I have the console open. So it's not just the dimensions of the screen itself. We've seen this before. Client width is going to update. Okay, so let's grab that variable, get bounding client rect, and we want dot right. So let's save this, const l right, element right. And let's rewrite our function before we go any further so that we don't have to pass in this absolute number. For example, 100, then 200, then 300, then 400. What if I could just say move 100 and then another 100, then another 100, and this would put us at 300 pixels to the right of the initial position. We would need to update this ever so slightly, so I'll just comment that out for now. For amount, we can keep that the same, but instead of just setting translate x to be that amount, we can calculate the current transform or the current position on the screen and then add to that whatever amount is passed in and use that to translate. So the current amount, if we want to find that, is right here. If we use get bounding client rect, we have the, let's see, left is 808. And then we have a little bit of, I believe it was margin or padding that added 8 pixels. It doesn't matter. We're not going to be super precise. I don't really care if this is going to be incredibly accurate. I don't want to get too bogged down. So let's use this left. So whatever the left is, we'll then add another 100 or 200, whatever the amount is we're trying to move. I'll make a new variable. I'll get the left and save that to a variable called current left. Then here, I'll just translate x to amount plus current left. So now when I call this, I hopefully can just say move 100 pixels at a time. It's easier. You don't have to keep track of if you've moved 100, then you want to move 200. If you want to move another 100, you have to add it together and do 300. Now I can just say 100 every time or 200 every time or mix it up, but I don't have to know how far we've already moved. Okay, so translate x. Let's see if it works. Refresh the page. It's working. It's moving 100 pixels every time. Okay, so now we can go back to checking if we've gone too far or if we're going to go too far. We have our boundary. We have the current right of the element. And what we want to do is check if that right plus, let's say we're moving 100 pixels. If another 100 pixels to the right is going to be too far and will be off the screen, then we don't want to move. So we could write a simple conditional. If element right plus the amount we're trying to move is greater than the body boundary, what do we want to do? Why don't we start with just console.logging done. And I apparently cannot type greater than. Oh, console.log done. Can't go, whoops, double quotes there. Cannot go that far. Else. We need the else. Otherwise, we'll just print this out and then run our code anyway. So let's add an else. We'll do the set timeout down here. Oh boy, okay. So we try and move 100 pixels every time, and if it's too far, like if I do the last one and try and move 500 pixels, let's see, we should move 4 times. 2, 3, 4. Oh, well, I'm an idiot. I moved the screen. Let's try and move 1,000 pixels. That should be enough for it to trigger. Okay, so 100, 100. And now we try and move 1,000. Perfect. Cannot go that far. Let's try one more time. And it doesn't move us any further. That's it. Okay, so that is working. We now have this situation where we don't move anymore. Otherwise, we do the set timeout and everything else, and we call a callback. Now let's go back to this idea of having a success and a failure callback. So I could pass in, here's what I want you to do if we can keep moving. Here's what I want you to do if we can't move anymore. For example, I could reset the position if we've gone all the way to the right, or I could just alert something. The way that we would structure this, and this is how a lot of older JavaScript libraries are actually written, they have 2 callbacks you pass in. So your request or whatever you're doing. Oh my gosh, autocomplete here. Here we go. And you pass in your success callback, which you wouldn't write like this, and then a fail callback. So those are 2 functions as arguments. So you would have your first function, do something, and then your second function, do something else. So let's try it. Let's rewrite this. So we have our first callback. Let's call this on success and on failure, or on fail. So down here, if we've made it to this point, that means we can keep moving. So we'll call if on success, which I guess we can just assume our code. Let's just assume that it will be passed in just to make our code simpler. We'll do on success right there. And on failure will be right in here. So now we have 2 branching paths. You try and move a certain number of pixels. If that number is too big of a gap to jump and you'll be off screen, this element will be off the screen, we'll call the on failure callback. Otherwise, we'll actually do that movement after some delay that you pass in and then call your on success callback. So now we have to rewrite this whole thing to have 2 callbacks every time. So I'm going to leave the original and I'll call moveX of our button. Let's move 100 pixels the first time. After 1 second, 1,000 milliseconds, this is our success callback. If we're successful, we'll do something. So I'll just write success. Then we have to add our second callback here. So a whole nother function. And this is if you cannot move, if this is too big of a jump to try and make. What do we want to do? Why don't we start with a simple alert, cannot move further. Okay. And so then if we're successful, we'll do another move X. This time, why don't we move 400 pixels? After 1 second, here's our success callback. We'll do something if success. I'll label these success, and then we have to add a fail callback to this function call. And already it's getting quite messy. So this would be our fail for the second callback, or for the second attempt. And here's our fail for the very first move X. So fail here, we'll do the exact same alert, cannot move further. And if I save, it gets all formatted funky. But this is a lot to just follow and try and read with your human eyes. It's really not pretty. And this is only 2 levels so far. Just adding in that second callback really complicates things. This is relatively easy to look at and understand. This happens, then after this callback will happen, then this callback. Here, when we have 2 callbacks at a time we pass in, it's just clunky and ugly. Okay, so move X button. Let's see, here's our success. Let's do one more. Move X. So if we move 100 pixels, we're still good. This is called. We try and move 400 pixels. If we're still good, this function is called. Otherwise, this fail is called. So move X. This time, let's do button. Something very large, like 700 pixels. That should do it for us, at least if I shrink my screen down. And then after a second again, here's our success callback. We'll just console.log. Really? We still have screen left, or something like that. And then we pass in our failure callback here. And this one will just alert, cannot move further. Oh boy, I mean, look at this. This is nasty to look at. But let's just see if it works. So every single time we call move X, we're now passing in 2 callbacks. The one to call if things work and we can move. The one to call if we can't move that far, we'll be moving off screen. And then as soon as we start nesting them, it just grows into this absolute spaghetti mess. So let's try it. I'm going to refresh my page. Okay, so it actually did work, but when I hit enter and close this alert, you'll see what it's kind of behaving oddly, or it might seem like it's behaving oddly. This is because of our set timeout and what's happening. If we go back, we're moving 100 pixels, then 400, then 700 if we can. But because this code is running right away, we're not doing it in the set timeout, it seems like we're stopping too soon. But as you saw here, okay, it stops, or it appears to stop, but I hit enter, it still moves. So that alert is actually coming from this move. When we moved over here, we could fix this problem if we move our conditional into the set timeout. Just to run through what's happening here, we're moving 100 pixels. But when we move 100 pixels, we're starting by checking, can we continue to move? All right, we can, so we don't run this, and we set a timeout. This timeout takes 1 second. If we pass in 1,000 milliseconds, it takes 1,000 milliseconds for it to run and then call on success. But as soon as that on success is called, this code runs immediately. This is not part of the 1,000 millisecond delay for the next time around. It's happening at the very beginning of the function. So we could rewrite this by moving this code into our set timeout. This isn't necessarily the best way of designing this. It might be better just to short circuit and just check as soon as possible if we can't move further, but this will make it easier to see when it's working for us. So now we're basically running the code at the exact same time. We're checking if we can go, and we're calling failure if we can't go. We're calling success if we can move, and we're doing it all within the set timeout. So now it moves again, and then it says, okay, I can't keep going. So we had the same outcome last time. It just was alerting us before we had actually moved. Okay, so this is looking great. It works, right? It's stopping when it should. If I expand my screen all the way over here, let's see. It now should be able to make that jump. And now we still have screen left, which is our success for our third move. So you can see this is quite ugly, and this is only 3 moves. What we had here was, 5 moves? So why don't I take a second to recreate this? I won't make you watch. I'll just do it really quickly, and through the magic of editing, it will be done. There you go. So I decided to change it to 300 pixel jumps because I know some of you will have wider screens or you won't have your console open like I have here. So I wanted to make sure in most cases that this would hit the edge of the screen. So I'm going 300, 300, 300, 300, 300. And then each time, if it fails, I have this failure callback. It's just alerting, cannot move further, cannot move further, cannot move further. Oh my gosh, can't talk. 5 times, I have to rewrite that code. I don't have an easy way of getting around this. I have to pass in that failure callback, even if I'm just doing basically the same thing every single time. And then on our last success, instead of continuing to move, I'm just alerting, you have a wide screen. So let's see what happens now. We move 1 time, 2 times, 3 times, 4, and then it stops. Cannot move further. And if I close my console, I think we'll be able to make it to the end. 3, 4, 5, and then the callback, which is you have a wide screen. Oh, okay. So this has been a ton. I know this is an incredibly long, dense video. I wanted to illustrate a situation where callbacks are useful. We have to use callbacks with what we know so far in order to write a function like movex, where we're waiting for something to finish and then running some code. We're using setTimeout all over the place in our source, as you see. Where are you? SetTimeout. And in order to make our functions work the way we've written them, we have to pass callbacks. So we have a onSuccess and onFailure. Remember, all of this stems from the fact that JavaScript does one thing at a time, and the browser is taking over when we call setTimeout. The browser is keeping track of time, and then it tells JavaScript, okay, time's up, run this function. And within this function, we have some logic, and then we tell JavaScript which one of these to run based off of some conditional logic. So this all stems from JavaScript's fundamental nature. The fact that it's single-threaded and we have these browser APIs, the web APIs, that JavaScript works with to make a request, to set a timeout, to set an interval, to add an event listener. The browser takes care of that and then tells JavaScript, all right, here's a function, here's a callback. That's great, but it can get really messy when we start having different outcomes, a success and a failure, which happens a lot when we make requests. This is a very simple example, but as you'll see shortly, when we make requests, real web HTTP requests, we follow the same pattern. We have some code to run when the request works. We have other code to run if the request fails. And so if we structure our code like this, onSuccess, onFailure, we have 2 callbacks, things get nested, ugly, and very difficult to follow quickly. I mean, look at how separated our code is. Yes, part of it is the way that my VS Code is formatting things, but even if we don't have all this indentation, it's still really difficult to know, if you want to change the failure callback for this first movex, you have to scroll down and just make sure you're at the right level, right? You have to, here's the first one, here's the second failure, third failure. It becomes hard to really follow and understand. So this is where promises come in. Promises allow us to rewrite a function like this, or this function here, so that we don't have to do all this crazy nesting. It's so much easier to read, and that's what we're going to see in the next video. So all of this has been set up for promises, but as long as it's been, this video I know is probably the longest video in the course, a real slog. I congratulate you if you made it here, and it will really help you understand why promises are worth it. Otherwise, if I just show you promises without showing you the struggle without promises, it doesn't do promises justice. So that's coming up next. Alrighty, so in the last video, we saw how using a bunch of callbacks and nesting things can get really out of hand quickly. This code is just long and difficult to understand when we're passing in 2 callbacks to each function call here, and they're all nested. There's a term for this, sort of a playfully loving term in JavaScript called callback hell. And you can see another example of this here on the left. Lots of nesting, lots of functions that are nested functions that are being passed as callbacks. This is just not very fun to write, and it's especially annoying when it gets really long and super far nested and indented, and it's just hard to follow. So this is where promises come in. Promises allow us to write asynchronous code that is much easier to read and understand. It's usually shorter, but even if it's not actually shorter in terms of the number of characters, it's much flatter often. It's not so nested. So here is where we'll end up. This code, written or rewritten to use promises, looks like this. a whole lot flatter, much easier to look at on your eyes, much easier to fix or debug something if it goes wrong. We don't have to figure out which callback we need to update. We don't have to, find the corresponding fail callback for this success. Thankfully, I have this bracket matcher, which helps me, but it's really obnoxious. So this is where we're going. It will take a moment, though, because we need to talk about the basics of promises. When we work with promises, there's really two different things you need to understand. The first is how you create a promise, how you could create a function that returns a promise. And then the second is how you consume or interact with promises, which we do all the time. Even if we're not writing the promises ourselves, we might be making a request from a library or using a library like Axios, which is something we'll see in just a bit. It returns, and a lot of its functions return promises. So we need to understand how we work with those promises. So we'll tackle both of those, creating promises from scratch, and then also just working with promises that someone else made. Okay, so let's talk about the basics. A promise is just an object. It's a JavaScript object which represents the completion or failure of some eventual process, something that can take time. Usually it's something that takes time. Otherwise, you probably wouldn't need a promise. So a promise is a way of promising a value that you may not have at the moment. Think of a promise in the real world. When I was a kid, I really wanted a dog. I asked my dad. He said, I promise we'll get you a dog if you get good grades. I got good grades, and, well, he didn't follow through on the promise until he had new kids, and then he got them a dog. But other people's parents would probably follow through on those promises and actually follow through and give them a dog, give the kids a dog. So a promise is different than saying, here is a dog right now. It's just a guarantee or a supposed guarantee of an eventual value or a dog or whatever we're talking about. So in JavaScript, promises are objects that represent an eventual either failure or success of some task that takes time. You make a request, if we use a library like Axios, which we will shortly, that returns a promise because that value, if you're making an HTTP request, that could take time and that value may never come back. It might be a failure or it might be successful and you might get some data back from an API, but it takes time. So the object that is returned in the meantime is a promise. And what we do is we attach callbacks to that object. So we don't pass in two callbacks or a single callback to a function and nest a whole bunch of things. Promises are objects that we can attach callbacks to instead. This may not make sense at the moment, but why don't I start by showing you how it works, and it should click after a bit of practice. So the way we make a new promise in JavaScript is like this, new promise with a capital P. I'll save this to a variable. Let's go with this idea of my parents promising me a dog. Const will get you a dog equals new promise. And when we create a promise, we pass in a function, and this function has two parameters always. These two parameters we usually call resolve and reject. And these are actually functions. And at any point inside of this function here, this function that we pass into new promise, if we call resolve, the promise will be resolved. If we call reject, which is a function like this, the promise will be rejected. Now, what does that mean for a promise to be resolved or rejected? Well, why don't we just start with doing neither? We just have our promise here. New promise, that's it. And we're not doing anything in it. Let's see what happens if I take a look at will get you a dog. I'll refresh my page. Will get you a dog is a promise object, and see that it has this one property called promise status, which is set to pending. So the promise is, it is a promise, but it has not been resolved or rejected. It has not been fulfilled, or it has not been broken, if we were talking about this idea in the real world of a promise. When someone promises you something, we would say the status of that promise is pending until either they break the promise or they follow through on it. So if we don't reject or resolve a promise, its value or its status will be pending. So the pending state of a promise is frequently what you will see initially when a promise is first returned. If we're making a request and that takes 10 seconds, which would be horrendously slow, during those 10 seconds, we don't have a response. We don't know if it's a failure or a success, if the response went to the right URL, if the server was up, if your internet was working. So it would be pending. But if I immediately call reject, which is a function, if I just write reject here, it's not going to work. I need to execute this function, reject, refresh the page, take a look. Uncaught in promise, we have an error that we didn't catch, and our promise status is rejected. And if I instead resolve like that, refresh, take a look at will get you a dog, promise now has status of resolved. So still not very useful at this point, but this is the most fundamental part of creating a promise. We call new promise, we pass in a function, and this function has two parameters, resolve and reject. You can name them other things, but this is standard. And when you call that first function, which should be called resolve, it resolves a promise. It fulfills it, and the status is set to resolved. And if we instead reject it, the status of that promise is rejected. Okay, so now why don't we make something slightly more interesting? We have will get you a dog. Why don't we write a promise that is randomly resolved or rejected? So that's pretty much the logic my dad used to decide if I was actually going to get a dog. I'm pretty sure he just picked a random number and decided, nope, there was no real rationale here. So why don't we pick a random number? We'll do const rand equals math.random. And then if rand is less than 0.5, we will, let's do resolve, else we will reject. So now this promise, every time I refresh the page, should be one of these states, either immediately resolved or immediately rejected, depending on that random number. So this time it was resolved. I tried again, resolved. Okay, now it was rejected. So this is the first part. This is how we create a promise. The next and also extremely important part is how we actually interact with a promise. How do I run code if this promise was rejected versus run code if this promise was resolved? This is where we meet our friend .then. So every promise has a then method. So we could call will get you a dog .then. And this .then method will run if our promise is resolved. So I have my .then and I'll pass in a callback. This code will run when this promise is resolved, and we'll console.log. Yay, we got a dog. So let's see if it works. Okay, so it was rejected. This code did not run. Refresh again. This time, if we take a look, it was resolved and our callback inside of .then was executed. Try it again, rejected, we don't see this code. There's no yay, we got a dog. So we have another method we can use with every single promise. We have .then and another one called .catch. Well, it's not called .catch, it's called catch. And we could just chain it on like this. We could also do will get you a dog .catch. This code will run if the promise is rejected. We'll console.log, how about a sad face, no dog. So if the promise is randomly rejected, this will print out. If it is randomly resolved, this prints out. No dog, it was rejected. As you can see, status is rejected. Once again, rejected, rejected, there we go, resolved. All right, so what we've seen so far may not seem that useful or revolutionary, but we've seen the two basic pieces of working with and creating promises. To make a promise, we call new promise. Every single time we pass in a function, and that function has two parameters, resolve and reject. Within this function, we can then call resolve as a function to resolve the promise. We call reject as a function with parentheses to reject the promise. And if we do neither, the promise will have a status of pending until it's either resolved or rejected. So that's creating a promise. Then we saw the .then or the then method and the catch method. Whatever we pass into then will automatically run when a given promise is resolved. And whatever we pass into .catch, the catch method, will automatically run whenever a promise is rejected. So these are two methods on a promise. A promise is an object. So this creates a new promise for us. And then here we're using two existing methods on those promises, or on this specific promise, will get you a dog. These are the basic building blocks of promises, and we're going to continue to build on these. Remember, we will be refactoring some code. That nasty callback hell we saw, was that the last video? Plus, we'll see how to make requests. This will all start to make sense. If you're questioning it, or if you're lost, it just doesn't seem that useful. This is not that great. I totally recognize that, but we have to start somewhere. So next, we'll continue on our promises journey. All right, so our current promise, "will get you a dog" promise, is either resolved or rejected immediately. There's nothing that takes time in this promise. There's no real reason to use a promise. We could just write a simple if else and just generate a random number on its own and print out code. Depending on if rand was less than 5, do this thing, otherwise console.log no dog. Pretty simple with what we've seen so far. But now let's introduce some delay, so it takes longer. What we'll do is just use a set timeout to simulate the number of years it took my dad to finally reject his promise of getting me a dog. So I will keep this here so we have a record of it, but I'll duplicate it. And then in here, instead of just immediately resolving or rejecting, let's do a set timeout. And our set timeout will have a function, and the delay will be 5 seconds. And then in that function, the callback, I'll move my logic to pick a random number and then either resolve or reject. So now this promise takes 5 seconds before it's resolved or rejected. Otherwise, those first 5 seconds, it's pending, which we saw earlier. So the .then code or the .catch code, whatever one of these runs, depending on if it was resolved or rejected, it won't run for 5 seconds. So let's try it out. I refresh. It takes 5 seconds. Come on. There we go. No dog. If I refresh and I quickly take a look at "will get you a dog," it starts as pending. For these 5 seconds, it's pending. Now it's been rejected. One more time. It starts as pending. Hopefully this time it's resolved. Nope. Okay, one more time. Come on. Come on. Resolve it. Get me a dog. Seriously? 3 in a row? How about now? It's pending. What the heck? Just resolve. Oh, the joy of you. Oh my goodness. How many of these are going to be in a row? Just resolve. Please. Okay, this is horrendous luck. Oh my. Pending. Oh, finally. I just hit the absolute jackpot of rejected promises. How many was that? Like 8, 9 in a row? Oh, what are the odds when I'm recording? But we finally get it. It starts as pending and then it's resolved. All right, so this is our first example of a promise that takes some time. It takes 5 seconds. It's kind of simulating making a request and having to wait for that request to come back. It's eventually resolved or rejected. Yes, we're just hard coding a 5-second delay for no reason, but imagine that something has to happen over those 5 seconds. Like we're animating something and we want to wait until the animation finishes, which we'll return to. That was the original impetus for promises in this section. We were doing a whole bunch of nested callbacks, and it was hideous when we were moving that button across the screen. So another thing that we frequently do is return a promise from a function. Instead of just making one promise like we have here, we could instead just get rid of my variable, define a function. We'll call this const make dog promise equals some function, and this function will return a promise. This exact promise we already have. So we just write return. So now I can call this function, instead of "will get you a dog," I can do make dog promise dot then, and I can actually just chain this on like that. I don't have to, well, if I call make dog promise again and did dot catch, that would be 2 completely separate promises. And they may not resolve, or they may not both resolve or both reject. They could have different values. But if we instead chain it like this, we get around that problem, and it's also just shorter and cleaner. You could save the variable or the result to a variable, d equals make dog promise, and then do d dot then and d dot catch. But this is just better. There we go. So let's test it out. We'll wait 5 seconds. Come on. And there we go. It was resolved. So nothing major that we saw here, except for the fact that 1, we can chain dot then and dot catch together without having to create a variable or without having to reference the promise again. I can just put a dot catch after a dot then, and only one or the other will run in this case. My promise is either resolved or rejected. if it's resolved, this function runs here. If it's rejected, this function runs here. And then the second thing we saw was that we can make a function which returns a promise, which is an extremely common pattern. Rather than creating a promise from scratch and saving it to a variable, often we work with functions where we would call, once we get to Axios, axios.get some URL, reddit.com. That will give us a promise, and we put a .then and a .catch after that. So this function itself is not a promise. We're executing a function which returns a promise, just like we did here. This returns a new promise. It's either resolved or rejected eventually. But in the meantime, it's still an object. It has a status of pending. And when it is either resolved or rejected, one of these will run. Okay, so we have a lot more to cover, so onwards we go. The next thing to know about promises is that when you reject or resolve a promise, you can reject or resolve it with a value, and you'll have access to that value in your callback that you pass into then or catch, which is really, really useful because most of the time we're not just waiting on some resolve or reject that happens arbitrarily, like a random resolve or reject. We want to know why was something rejected, for example. In the case of a HTTP request, why did this fail? And if it didn't fail, if it was resolved, what is the data that we got back? That's the point of making a request, at least most of the time, is you're trying to get some information. So we are going to make a fake request function here. We'll call it const fake request. And we'll pass in a URL. So we'll call this like fake request reddit.com or something. Or actually, let's just do relative URLs. So /dogs or /login. And it's going to take some time. So we know that. It's going to return a promise because it takes some time. So let's do return new promise. And then we have our callback in here. I think it's called an executor function, and on the docs at least. It doesn't really matter, but we have our resolve parameter and our reject. And then we'll do a set timeout. And how long should this timeout take? Let's say it takes 3 seconds to make a request, which is a pretty long time to make a request. And then our callback that goes here for set timeout. And what do we want to do in here? Let's pick a random number and decide randomly if this request worked or not. And we'll resolve it or reject. So sort of the same thing we've done before, math.random. We'll save that to a variable, const rand. And then we'll check if rand, we don't want it to fail half the time. So let's say if rand is less than 0.3, we will reject to start, just like this. And then else, we will resolve. So far, nothing new. We've already seen how to do this. If we call fake request, we don't even need to pass in a URL because we're not using it at the moment. So fake request dot, let's just do a dot then, a simple one, and a dot catch. We will console.log request worked. And then in our dot catch, we'll do a console.log request failed. So this is kind of a recap of what we already know. It's the same idea, a set timeout, faking something. In the last video, we were doing a dog promise, but it was the same thing, except I think it was a 50-50 chance. Now we have a 30-70. So if we run this, it should take 3 seconds, and we'll see either request worked or request failed. And I won't keep going. Hopefully we get a request. Okay, one more chance. Give it one more chance. All right, well, you'll just have to trust me. Request will fail at some point. So this video is about how we can reject and resolve with a value. We can pass information in to the resolve or reject calls. So let's start with reject. If we reject, why don't we pass in a status code? So a typical HTTP response includes a status code. You've probably seen 200 for OK, or you've definitely, most likely at least, seen 404 not found. Why don't we just pass that through? So reject, and then let's pass an object in where status is set to 404. So now, instead of our catch, if something is rejected, our callback instead of catch will run. So we can add a parameter in now. We could call it data or response. And then we can look at res.status, console.log res.status. And if this ever fails, let's do 1 second just to make it easier. Come on, it worked. Okay, there we go. 404 request failed. So we have access to this data that we pass through. Just a single variable, or it's not even a variable, a single value. We could pass more things, like reject with this object, and then I don't know what else would make sense in this context, but we could put whatever we want in here. We could also pass in 2. And then we just have a second parameter. We could call it num. Now, as far as resolving with a value or multiple values, it's the same process. Why don't we do something a bit more useful? Like when we call fake request, we'll pass in a URL. How about /users? And then we'll use that URL to decide what to respond with. We're pretending to be an HTTP request. We're mocking it out. We're adding the delay. Why don't we start with a variable? We'll call this, what should we call this? Maybe data or pages? Sure. It will be an object where we map a URL like /users to some information. And how about our users will be an array of objects where we have an ID for each one. Let's just say ID of 1, username is Bilbo, and we'll just have 2 users in here to keep it simple. ID of 5, username will be, how about Esmeralda? Okay, so whatever URL is passed in, we will use that URL parameter to access information out of pages. Let's just add a second page in here. This one will be /about, and it will just be a string of text. This is the about page. Okay, so if you pass in /users, what we'll do is take that URL and resolve with pages of URL. Let's just call this data, const data, and then we'll resolve it with an object maybe, so that we can include a status code of 200, which means okay, and then we'll also include data. And I'll just use the shorthand instead of data:data, we'll just add data. So if we check it out, we pass in /users. Let's start with something easier. How about /about? Then we'll go with response, maybe res again, and we'll console.log. Let's go with status code, res.status, and then duplicate that and do res.data, which is the second thing, right? We have status and data that we resolve with, and we'll go with data here. Let's see what we get. If it does resolve, and it did, status code 200, data, this is the about page. Now, instead of randomly resolving or rejecting, let's get rid of the random number. And instead, we'll reject if the URL is invalid, if it's not contained within pages. So we'll get rid of all this, or almost all, I'll just get rid of all of it. And what we'll do here is check within the set timeout. So we're still going to wait a full second or 3 seconds or whatever. We'll check if the URL was in pages. So if data, right? We're just plugging this URL in. If data, we will resolve with this that we already have, else we'll reject with the object that has status set to 404, which means not found, which makes sense. The URL you passed in was not found in our fake application. It has 2 endpoints right now. Why don't we test this out now? So if I do about, we'll see if that one works. It should still work. I'll change it to users actually. And then if we try another one, this time, fake request, we'll do /dogs, which does not exist in our pages. So if the URL is dogs, this line should be undefined, so this won't run, and instead we'll reject. Let's double check. Cool, so our first one worked. We got status code 200 from the .then callback right here. Res.data were these 2 users. And then the second request did not work. We got 404 request failed. Alrighty, so in this video, we saw that we can resolve and reject with data. We can pass through some argument there. In this case, it was an object in both resolving and rejecting scenarios. And then inside of our .then callback, we can add a parameter, give it whatever name we want, and it will have that data. It will be passed whatever the promise was resolved with. And then same thing for .catch, except when the promise is rejected, this function will run, and this parameter will have whatever value we passed. All right, so we're almost done with the basics of promises. We have one other really important topic to cover, which is chaining multiple promises. What if we wanted to make another request after the first one we have a really nice way of doing it. So that's coming up next. All right, so the last really critical part of promises is understanding promise chaining. So I've updated the fake request function to now have a much more robust set of pages. It's still pretty minimal, but we have a couple different endpoints. We can make a fake request to /users, which would give us something like this, where we have an ID for each user, and I could use that ID to make a second request to get more information about a user. And this is actually a really common pattern, where a website or some API is set up with some endpoint that gives you a little bit of information about every user or every, I don't know, dog in the dog shelter, or every post on the Reddit homepage. Then it gives you an ID that you can use to make a second follow-up request using information from the first, so that you can get more detailed information like I have here. So if we wanted to mock that, we would make a request to /users, a fake request, and get this information back. Then we could take this ID of 1, and make a request to /users/1. But we want to do that after this one finishes, after we know for sure what that ID is, just like we would in the real world. So if you pretend for a moment that this is real, it's not just a fake object of pages where we're just hard coding the data in, those IDs could change. There could be users that are deleted. So we would ask for all users and then make a request to users/1. With what we know right now, here's how we would do it. Fake request, and then the URL, let's start with /users. Then we have our callback, which gives us a response. And then what we would do is take a look at response.data. That is the name that we used, right? If we come down here, data, and we want the ID right here, this ID of the first user. So the array is what we get back. That contains 2 items. If we just console.log res.data, let's just pretend that we are on a journey with a real API. Here's what we get back, an array. So if we want to take the first user, that would be console.log res.data 0. If we want that ID, we could save that to a variable. Let's just make sure we're printing it out correctly after 1 second. Okay, so let's save this to a variable. We'll call it const ID. So we have the piece of information we need to make our second request. With what we've seen so far, I'm not printing anything. Well, I'm an idiot. Nothing will show up. But with what we've seen so far, we would have to just make another call to fake request. We have to do that either way. We can't get around that. But we would nest it in here because we need this to happen after this one finishes. So logically, it would go in the .then. If we put it down here, it's not going to happen afterwards. We depend on this ID, which we only have access to in this callback, the .then callback, where the response is passed through. So I have to do it in here with what we've seen. I would call fake request again, and we'll use a template literal to do /users/ and then $ curly braces, my ID I got from the previous request. And I could do a second .then, same exact thing, res, and then we can console.log the response. Let's see what we get. So we should get a first, actually, we're not printing the very first time. So we only see the second response that we get back, and it has more information about the user with ID of 1 and status of 200. This all looks good. If I wanted to make another request with that, if we look at the data we got back, we have this top post ID. So I now can send a request to another URL I've set up in my pages object called /posts/ and then this ID. So I could then make another request, fake request, and it's res.data. What was it? Top post ID? Yes. So this is a third request that is dependent upon the second request, which itself is dependent upon the data we got back from the very first request. We got all users. That gave us an ID we could use. We used that to make a request using that ID. Now we get this top post ID, which we can use to make another request to /posts/some ID. So we'll do /posts/ and we'll save this to a variable, const ID again, or how about post ID? And then interpolate that with $ curly braces, post ID. One more .then, we'll get our response. hopefully. And then we'll do our console.log response. Okay, we'll try it. Come on. All right, what do we get back? Yes, we're getting our post information. Ladies and gentlemen, may I introduce you to my pet pig, Hamlet. So this was some hypothetical post on our website by this user. So what we have here doesn't look much better than what we saw in the whole callback hell section of this section, where we talked about nesting a whole bunch of things. Also, we don't have catches right now. So if I wanted to do that, it gets even messier. If I want to catch, I would do .catch, pass in my callback, and we'll just call this error, and then console.log, oh no. And then we'll also just print the error. So right now, we don't have a way of causing an error, but if I mess up this request and I use a wrong or an invalid URL like that, it should catch it. And it does. We get, oh no, here's our error. It's a status code 400 or 404 in an object. But if this one is valid and I instead mess this request up, this is a URL that doesn't exist in our pages. Let's see what happens. It didn't work. I mean, the promise was rejected, but we didn't catch it like we have here. So this catch is only working for this fake request. So I would need another .catch for this .then. So we have a much, much nicer way of rewriting all of this. What we're doing here is essentially the same thing we saw with callbacks, where we just nest them and nest them and nest them. This fake request is dependent on the data from this one. This third one is dependent on the second one. So it makes sense to nest them. But we have a whole different way of structuring them. What we can do instead, I'll just type this sort of in a shorthand up here. If we do a .then, and in the callback of the .then, we return a promise, we can call .then immediately after on the same level. I don't have to nest. I can chain it. And I can continue to chain as long as each callback for .then returns a promise. I won't nest my .thens. I won't have to do any nesting. Instead, I return a promise. This .then runs first. It returns a promise. This .then will run if the second promise, the returned promise, was resolved, and so on. So let me show you what that would look like. We have our fake request .then, and then we have this whole callback here. We get the ID. Then we have our second fake request here. What I'm going to do is remove all of this right here and return this function call. This returns a promise, just like this did. Our function, the first line says return new promise. So this returns a promise. We're putting the .then on that promise. Then inside this .then, we return another promise. And what I can do is put my next .then on the same level. So here I am doing another .then, getting the post ID from the response. I can return this fake request, which returns a promise. And I can move my .then outside. So if you look at my code now, I should have saved the original where we were nesting things. It was .then, and then inside that .then, we essentially had another .then, and then another .then, and we didn't even bother with catches. That was still a lot of nesting. Now what we're seeing, if you take my word that this does work, is that we can write things in a much more linear way. So do this, then do this, then do this. So this will only run if the first promise was resolved, meaning this ran, then that promise that was returned, the second promise was resolved, meaning that this code runs in the .then callback, and this promise is resolved, which would trigger this callback. So if any of those screw up at any point, and this is a real magical part, we only need one .catch. So this .catch will run if any of these promises are rejected. We have this promise, we have this promise, we have this promise. We only need one .catch. It's like a catch-all. It's really, really nice. So right now, we do have an error here. It won't work. So let's just start with it actually working. So users, then users / the ID, then post / the post ID. Let's see what happens. I'm going to console.log the data we get back each time. So console.log res, I'll do that here, and you'll see them happening one after another, even though they're not nested. Oh, I'm doing it twice here. Okay, moment of truth. We get our first one, second one, third one. pretty cool, right? We don't have to nest. These take time, but we don't have to use a bunch of callbacks and continue to nest and get crazy with that multi-level craziness. Yeah. All we have to do is make sure we return a promise inside of this callback, and then we can just add another dot then. We could have as many levels as we want. Remember, like I already said, this is only going to run this dot then if this promise was resolved. And this one is dependent on this promise being resolved. This one is dependent on this one. So it doesn't look like we have this crazy multi-level dependency thing going on, but that's the magic of promises. We can rewrite our code in a much easier to read manner, right? Do this, then do this, then do this, then do this. If at any point something went wrong, do this. So why don't we have something go wrong at the beginning? We'll use a URL that doesn't exist. Oh no. Okay, so the catch ran, that callback. Now let's have something go wrong here. So we have our first promise that should be resolved. There we go. Then we get, oh no. And this code never ran, right? When we had an error with the very first one, none of the other dot thens ran. It went straight to dot catch and it was done. But now if I have an error in this third request, we get the first two resolved, rejected, dot catch runs. So hopefully you can see already, even though we're doing very fake stuff, it's a mocked request, it's hard-coded, it's stupid. I won't say stupid, it's useless in the real world. It's useful in an educational context. Even though all of that is true, it's still a good illustration of the benefits of using promises. We can have multiple asynchronous actions that we want to happen one after another. So not simultaneously, but one after another. We chain dot thens as long as we return a promise each time. Everything works, and we only need one dot catch. So what we're going to do next is revisit the early example that I used to illustrate callback hell, where we were moving a button across the screen. We'll rewrite it with promises, something slightly more useful instead of just an arbitrary fake request. You'll see how much time, you'll see how much code it saves us and how many headaches it prevents. It's so much easier to read. So that's next. Now that we're relatively comfortable with promises, let's try and refactor this little demo from earlier, where we had a button that was moving and eventually running out of room potentially and stopping. So if we can't go further, if we can't go whatever 200, 300 pixels, whatever the jump was, let's see, I think it was 300 pixels. Yeah, so if we can't go another 300 pixels, it stops. And we achieve this by using a bunch of set timeouts and then changing the transform property of the button. But every time in that set timeout, we would check, do we have room to move? If we don't have room to move, we would call one callback that was passed in, the onFailure callback. If we did have room to move, we called the onSuccess callback. So we ended up passing two callbacks in every time we call moveX. And if we wanted the first one to complete, the first move of 300 pixels before the second one started, we have to use these callbacks. With the way that we've set it up without promises, it's a bunch of nesting. A whole bunch, as we saw. Very, very painful. So let's rewrite this using promises. I'll comment this out so we don't get the original movement going on. And I'll also duplicate this and comment it out. And then I guess I'll do it at the top here. We're going to refactor moveX. It's going to no longer accept an onSuccess and onFailure. It's going to instead return a new promise. Remember, this promise takes a function as its argument, resolve and reject, which are also two functions. And then we can move this logic from before into our promise, executor function. Maybe I'm making that up. I'm pretty sure that's what it's called, but inside of this new promise function. So instead of calling onFailure, we would reject the promise if we can't move. We're calculating the end of the body, how many pixels we have, let's say 900 pixels or something. Actually, we can see it's telling me I'm at 1225 pixels. Then we're calculating the right of the button and then the current left of the button, which we use if we are going to move. And we want to check if the right, whatever, let's say 800 pixels plus the amount we're trying to move, 300 pixels, if that is greater than the boundary, we'll reject, meaning stop. We're not going to continue. Otherwise, instead of on success, we'll call resolve. So very similar code, except we've wrapped it in a promise that we're returning. And we're not passing in 2 callbacks every single time. So now how would we use this? It would look like this. Move x of button. Let's do 300 pixels and the delay of 1 second. Dot then. And we're not passing any value in when we are rejecting or resolving. We could possibly, maybe when we reject, we could include a reason. We could include the, maybe the current position of the element. We could do something with it. And then we've got our dot then. Why don't we just console.log done moving and start there. So I'm going to refresh the page. It moves and we get done moving. Okay, so if we wanted another move x after that first one, like we had before, we move 300 pixels, we move 300 pixels again 1 second later, we don't have to nest it. All we need to do is call move x again, move x button 300 pixels over 1 second, not 2 seconds. And if I wanted another dot then, yes, you could do this, put it inside the existing dot then callback, or we just return this promise. This gives us a promise now, which is what we saw in the last video. We can chain promises, and I can put another dot then here, and now I can console.log done with both. Okay, so we do the first thing. That takes some time. When it finishes, when that 1 second is over, the button has moved, assuming it has room, which it should. We're only going 300 pixels. Then we're going to move x again, which will return a promise. It may or may not be completed or resolved, depending on if we have the correct number of pixels, the correct space to keep moving. And if we do, this dot then will run. We don't have a catch yet, but this should be good because we're only moving 600 total. And then we get done with both. So that only prints out after 2 move x functions are done. Both promises have been resolved. So now if we wanted to do like 5 of them, all we need to do is duplicate this a couple times. So now we're moving 4 times. First 300 pixels, it takes a second. As soon as it's done, but not sooner, as soon as it's done, then this runs. And then as soon as that finishes and hopefully is resolved, this runs, then this runs. We don't have a catch yet, so we may run out of space. 300, 300. Are we out of space now? Yes. Uncaught. So we had a rejected promise, but we didn't catch it. And as we saw, all we need is 1 dot catch. And we'll console.log. Console.log out of space cannot move. And we should see, one more time, here we go, outer space cannot move. And if I instead changed it so we're trying to move like, 3,000 pixels on the third move x, we'll still have the same catch work. It will catch that promise which is rejected. It will catch the error. So let's try that. First jump, second jump, third jump can't happen. Outer space cannot move. Now what's really cool is in situations like this, where all we're doing in the dot then callback is returning another promise, we can shorten it up. As we've seen with arrow functions, if you do choose to use arrow functions, if you are returning something and it's the only expression, the only line, you can use an implicit return. So you could use parentheses. We don't have to write the return keyword. You can just do this right here, just like that. And we can chain them together. So I'm just going to replace what I have with a couple of these. Let's do 5 of them and keep our 1 dot catch. So this only works to make it super concise and just nice, not a bunch of curly braces. That only works if there's only one expression and it should be returned implicitly. So we don't write return, but it's being returned. If you need some review on that, check out the arrow function section. Okay, so let's check it out. First move, second move, third, fourth, and then we run out of space. Awesome. So I could change this to be 100 pixels and do this a whole bunch We'll see when we run out of space. One more time. Is that still? Oh, I guess we're moving 300 the very first time. I didn't change that one. And now we're out of space. Pretty cool stuff, I think. It's a really nice way of shortening your code up and making it, it's not even about shortening it, it's making it just easier to follow. If we compare, this is a huge mess. Not only is it nested, but we had to pass in 2 callbacks. So we get this ugly, I don't know what to call this, like a triangle, a pyramid, mirror image, the reflection, there we go, of all of these callbacks, even if they're doing the same thing, the failure callback. Here, we just need a single dot catch, and it does the trick. So the last thing we could do is refactor this a bit. So our dot catch could actually know, this callback could know where it was stopped, why we didn't keep moving to the right. Basically, we know we're out of room, but we could, print out the button is currently at 500 pixels and you tried to move 300, but the body is X, or who knows. We could just make a little object when we reject that included, let's say, the body boundary. And I'll just use the shorthand here. So body boundary will be the key and whatever it holds will be the value. Let's also add in the element right and the amount. So we'll have 3 different properties that we are passing through when we reject. Then down here, when we catch, we can just add in our object. We'll just call this, you can call it error, but it's not really an error. We'll call it data as a parameter. And let's grab, we could just destructure actually. If we want body boundary, we want amount, and what else was there? L right. Okay. So we can console.log something like body is, let's do template literal, string template literal, body is body boundary px wide. And then below that, console.log, let's say element is at L right px, comma, and then we'll display the amount. Px is too large. Okay, so we reject with that information rather than just blindly or always printing out of space cannot move. Let's see what happens when we finally hit that catch. Oh, I forgot I did all these 100 pixel little tiny jumps. Okay, here we go. Body is 1354 pixels. Element is at 1297. 100 pixels is too large because that would take us to 1397. And that's pretty much it. So still a very simple example, not the most useful thing to do ever, but you can see what a massive difference this made. I mean, we're doing, 10, 15 different calls to move X, and they're happening one after another, and all of them are handled. If something goes wrong, if they fail, we don't have room, this catches all of them. Compare that to this. This is only 5 or so different move X calls. If we wanted to replicate this, I would be here forever. We would have at least twice as much code as we have right now, and it would be incredibly nested and hard to keep track of. So that is a real value of promises. It's not just about doing asynchronous things and being able to run some code afterwards. It's also about being able to catch. Anytime a promise is rejected, having a single catch, it makes a huge difference. We don't have to have 10 or 20 different catches, one per each .then for each promise, as long as we return a promise in the .then, which is what we're doing thanks to an implicit arrow function return. All right, so we're now moving on from our sort of playland promises where we're doing very, very trivial, simple things. And next we'll move on to making real HTTP requests and use promises. Those functions, those methods return promises. So we'll get practice with all this fun stuff that we've seen so far.